section 6.5 least square problems. What's the goal behind this section? We learned in the past when you're solving systems of equations, we have three cases. Either you get the consistence where there's only a single solution, or the system is also consistent but there's infinitely many solutions and there's a free variable, or it could be inconsistent where there's no solution. Okay, so our main concern today our goal here is to look at the equation or the system when there is no solution. What happens in this case? Do we just say no solution? Well, yes, but in the real world situation, this can be not sufficient, or you can say, we say not sufficient. So what happens in this case? Instead of leaving this equation ax equals b has no solution, we want to do an estimation. We want to find an estimation. So we want to find what we call x hat, so that ax hat is as close as possible to vector b. Okay, as close as possible to vector b. And this is true since b is not in the column space of A. It's not in the column space of A. So what we need to do here, is, let's say, let B hat, instead of B, vector B, we're gonna have B hat, belongs to the column space of A. Okay, that is the closest to vector B. Since B hat in the column space of A, then there exists an x hat, so that ax hat equals to b hat in that sense. So let's say the geometric intuition for this is the column space of A. Vector B is not in the column space of A, as you can see. Instead we have B hat in here, and this one here is B minus B hat. So what we are doing here, we're thinking projection wise. This is 90 projection, and that's what we did in the last several sections. So x hat in this case is called the least square solution. So this x hat is the vector that gets us very close, or the closest to B, or vector B. Again, B hat is the projection of B onto the column space of A. Note, B minus B hat is orthogonal to B hat and to any vector in the column space of A. So we start here by introducing a definition just to give you an idea. If we have a square matrix A, n by n square matrix A, and B is in Rm, a least square solution of Ax equals B is a vector x hat, as we said, in Rn, so that the distance between B minus Ax hat is less than or equal to B minus Ax. Means the distance, this is the shortest distance. So if you want to draw like if you want to draw another diagram, this is the column space of A, and let's say that's vector B. Okay, so if you project this down, this is going to be Ax hat. But for any other x, maybe you have Ax here, or maybe you have Ax there. So Ax hat is the projection. So think about it as the closest distance. The closest, it means the perpendicular distance. That's what this is saying. The distance between B and Ax hat is less than or equal B and Ax, where x any vector in Rn. Again, as I said there, for any vector in Xn, Ax belongs to the column space of A. We want to find x hat so that Ax hat is closest point in the column space to B. Again, we get the least approximation. We are approximating here solution x hat by solving the equation Ax hat equals B hat. And B hat is the projection of B on the column space of A. Now we introduce a theorem that says the set of least square solutions of the equation Ax equals B satisfies the equation A transpose Ax equals A transpose B. It's kind of like you multiply both sides by A transpose, and we're going to see how that helps us to get the approximations. And this equation, the latter equation, presents a normal equation for this, and I'll show you what that means here. But we need to look at the proof of this. When we look at the proof, it helps us to see where this came from or why we're doing this. So again, a lot of this is if x hat satisfies the equation Ax hat equals B hat, B minus B hat is orthogonal to the column space. We said that earlier. Then B minus B hat is perpendicular to each column of A. Okay, each column of A. And I'll show you what that means. So therefore, B minus B hat is perpendicular to each row of A transpose, because A transpose is obtained by switching rows and columns. The row becomes column, column becomes row. Now, before we look on the left-hand side, let me write something down just so you understand. Say A is this matrix A2 all the way to AN. So these are the columns of A. Then, since these vectors A1, A2, AN, all of them are in A, then if you take each one of these vectors AI, okay, and you dot it with B minus B hat, this should always give us 0. Since each one of this in the column space of A, and B minus B hat is orthogonal to the column space of A. This means B minus B hat is orthogonal to every vector in the column space of A, and therefore the dot product must be 0. So now we go back to this A transpose, right? So what is A transpose? A transpose becomes A1 all the way down to AN. like that. So if you take A transpose dotted with B minus B hat, that should give us 0. So A transpose A1 all the way to AN dotted with B minus B hat, that should give us 0. So on the left hand side, we write it like this: B hat is AX hat, and if we multiply this in, what do we get? A transpose B hat B minus A transpose A X hat equals 0. If we add that to both sides, that gives me the equation. We get A transpose B equals A transpose A X hat. So this helps. This is like a method or a strategy, helps to find AX hat. And from here we can find X hat. So the least squares solution satisfies this equation. It helps a lot with calculations when it comes to finding X hat. So now we move down to this example. Find the least square solution to the inconsistent system AX equals B, where A is given and B is given. So what do we need to do here? We need to find X hat, vector X hat, which is the approximation, okay, is the approximation we're looking for. So to do so, we need to calculate A transpose A and A transpose B. A transpose A and A transpose B. Why? Because of this equation. So we said A transpose B equals A transpose A X hat. So to find X hat, we need to find this one and this one. And then from there, we can solve for X hat. What is X hat here? It's going to be a vector in this form, x1, x2. x1, x2. So to find x1, x2, let's see what we need to do. Again, we need to find A transpose B. So A transpose, you just take A and make rows, columns, columns, rows. That's what I did. And A stays as is. Then multiply row by column. Row by the next column. The next row by the first column. Next row by the next column. And that gave me this. And you can test it out. It gave me 8, 4, 4, 5. So I found A transpose A, and now we need to find A transpose B. So I took A transpose and I multiplied by B, the given vector 1, 2, 3, and that gave me 8, 8. So notice I need again A transpose B. The equation says A transpose B equals A transpose A times X hat. So I found what this is, I found what that is. I'm going to substitute them into this equation. So we call it normal equations. So A transpose A X hat equals A transpose B. So I substitute them in, and remember X hat is X1, X2. So now, to find x hat, we do keep, basically, it's not like moving this to the other side, but we multiply by the inverse of that. This is the inverse. So we take what we got for A transpose A and we find its inverse. So if you have a matrix A, B, C, D, to find its inverse, we do 1 over, called matrix Q, 1 over the determinant of Q times, we swap A and D and switch the signs of B and C. So now I found the inverse for that matrix 8, 4, 4, 8, and I got 1/3 comma, or 1/3 4/3. This is the least solutions. This is x hat. So let me show you more information about this. Remember how originally the question was to solve ax equals b hat, ax equals b, right? But then we did an estimation to get ax hat equals b hat. So we found x hat. So let's take A. What was A? A was 202, 012, 202. And this one we found it 1/3 and 4/3, right? So 012, so that's 012. So if you multiply this, let's see what we get. Row by column. 2 times this is 2/3 plus 0 2/3. Next row by the next column, by the same column. 0 times 1/3, 0, 1 times 4/3, 4/3. Next one, this by this, 2/3 plus 8/3. That's 10/3. That's what we got. Okay, that's ax hat. And notice, what was B? B was given as 1, 2, 3. So this is B hat. I want you to compare these two together. You know, the 1, 2/3 very close to 1, 4/3 like 1 point something something close to 2, and 10/3 3.33 something, which is close to 3, right? So that shows us how close B hat and B to each other. It's good to know. We can calculate the error, we call it. And what's the error? Let me write it down here, is B minus B hat. So B here was 1, 2, 3, and B hat is 2/3, 4/3, 10/3. So then you find the magnitude. That shouldn't be that difficult to do. 1 minus 2/3 is 1/3. 2 minus 4/3 is 2/3. 3 minus 10/3, negative 1/3. and that would be the square root of the first one, 1 9 plus 4 9 plus 1 9. 4 5 6 over 9, 6 over 9 by 3, 2 by 3 3. That's the error. Now observe when A transpose A is invertible. Okay, from this equation A transpose A x hat equals A transpose B, the equation that we used earlier, we called normal equations, we can solve for x hat by multiplying both sides by the inverse of A transpose A. So that gives me x hat to be A transpose A inverse times A transpose B. And this is actually a theorem that says the matrix A transpose A is invertible if and only if the columns of A are linearly independent. And in this case, the equation AX equals B has only one least square solution, x hat. And that solution is given by this equation. And just in general, when a least square solution x hat is used to produce, let's say, ax hat as an approximation to B, to vector B, then the distance from vector B to ax is called the least squares error of this approximation. If A transpose A is not invertible, what happens? We need to solve for the reduced row echelon form of A transpose A. And one thing important to keep in mind, to note that A is not always a square matrix, right? So in this case, A transpose A inverse does not always equal A inverse A transpose inverse. So this only works if A is always a square matrix. Just keep that thing in mind. There is another way to find or to calculate the least square solutions. We'll see if we have time to go over it. So note there might be more than one possible least square solutions in this case. And for example, when the normal equations have free variables, then the least square solutions is not unique. And hopefully that will answer the question in the chat. Okay, so now we can put all this together, all the stuff we talked about, linearly independence, unique solutions, stuff like that, and come up with a theorem that says if you have A, which is m by n matrix, not n by n, m by n matrix, the following statements are logically equivalent. The first one, that Ax equals B, the equation, has a unique solution or a unique least square solution for all B in Rm, m, the number of rows, is equivalent to say that the columns of A are linearly independent, and it's equivalent to say that A transpose A is invertible. this case, when these statements are true, then the least square solution x hat is given by this equation that we showed you earlier. The inverse of A transpose A times A transpose B. Now we can look at alternative calculations, alternative way to calculate the least square solution. And then that can be done using an example. A is given and B is given. We need to find the least square solutions. So what's the alternative way? The columns of A, matrix A, we call them A1 and A2. So there are two columns. One thing to note about these columns are orthogonal. Those are orthogonal. If you multiply 1 times -6 plus 1 times -2 plus 1 times 1 plus 1 times 7 and add them up, that gives you 0. So the columns of A are orthogonal. In this case, we use what we learned in the previous sections, that the B hat, which is the projection of B on the column space of A, can be calculated by taking B dot A1 over A1 dot A1 times A1 plus B dot A2 over A2 dot A2 times A2, because there's only two columns, so we have two sets. So you know how to multiply B times A1, multiplying x by x, y by y, z by z, w by w. So 1 times -1 plus 1 times 2 plus 1 times 1 plus 1 times 6, that gives me 8. And if you do A1 dot A1, you get 4. Same thing with B dot A2, you get 45, and A2 dot A2 is 90 times A2. Simplifying this, 2 times A1 plus 1/2 times A2. That's B hat. If we calculate it and simplify, that gives us -1, 1, 5/2, and 11/2. So now we solve for x hat using the equation A x hat equals B hat, because we have A and we have B hat. So we just have to find x hat. So the answer should be 2, 1/2. Right, so to calculate this, x hat would be, if you multiply both sides by A inverse times B hat. Or sorry, times B hat. And you know, to find the inverse of A, it's not that difficult. Is that how you guys did it? Also, you can look at what I said, the weights of the B hat combination form, these ones here. Okay, the 2 and 1/2. Those are the same as the 2 and 1/2. That's the easiest way to get that. And the last thing to do here, we introduce a theorem which says also to help us to find least square solutions. So given n by n matrix A with linearly independent columns, we let A equals QR be a QR factorization of A from the previous section. Then for each vector B in Rm, Ax equals B has a unique solution, or a unique least square solution given by x hat equals the inverse of R times Q transpose times B. I'm not going to prove the theorem, but at least we need to see how to use it. So if we look at this example, A and B are given. We need to find the least square solution of this equation. So let's see how we calculate this. So again, A equals QR. How will we find that out? We need to find Q and R. Do you guys remember from the previous section? I found Q and R from the previous section. As you can see, this example, how you find Q and R, we go ahead and take x1, x2 as the column vectors of A. Using the Gram-Schmidt process, we let v1 always equal x1, and then we used x2 to find v2, and after we found v1, v2, we normalized them, and that gave us an orthonormal basis. Those two vectors, the normalized vectors u1 and u2, they form the vectors of Q. And after we found Q, from Q we could find R, because R is Q transpose times A. Q transpose times A. That's how we find Q and R. So back to this one, that's how we found Q and R. I didn't show the process here, but it's easy to do it using the previous section. From here we found what Q transpose times B, because B is given, and from Q I found Q transpose. We did some row operation by multiplying row by column, and that gave me 17 halves and 9 halves. Then from Q transpose B and R inverse, it's very easy to find R inverse. We could multiply everything out, again using row operations. And that gives us 2.9, 0.9. So that gives us x hat that we're looking for.